Hello, and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM 6. The topic for today's presentation is 2024 NDS 2021 SPDWS timber shear wall design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Cisco Cho will be your moderators, answering any questions you may have. They are both support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way with the GoToWebinar, you can go ahead and control these settings as shown here. We also want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So I do want to quickly go through the content over the next hour today. I will preface that I'm going to go about 5 to 10 minutes over. So if you do need to drop off at the 1 hour mark, no problem. Just wanted to give you a heads up on that. But we'll first begin with a quick introduction to what is a timber shear wall. Take a look at the various elements that comprise these walls themselves. We'll then move on to our example modeling within our program RFEM 6, considering both with and without openings. We are going to be utilizing the multi-layer surfaces add-on. So this is required in order to automatically generate these timber beam panels. We will also be utilizing the timber design add-on. So the RFEM 6 program will go ahead and run the analysis for us, but we want to take this a step further to also carry out the design according to the NDS and the SDPWS code, and we do so with this additional add-on. Of course, through these examples today, we'll take a look at the detailed analysis and results overview, and finally, we'll conclude today with future developments related to our timber shear wall. So for those of you joining us today, I'm sure most of you are familiar with what is a timber shear wall, but we'll go ahead and show here the basic framing elements. So we're talking about the inner studs, the end studs. We have top and bottom plates as well as the openings. So in addition to the framing elements, we also have our sheathing. So this is typically OSB or plywood, for example, in panel widths of 4 feet. If we have these various panel widths, we additionally are going to have this sheathing joint. Now we connect the sheathing, again, either OSB or plywood, to the framing members with typically some type of fastener. And within the US, we're usually connecting these with nails. We also need to essentially anchor our shear wall to our foundation or to our floor, and we do so with an anchorage system such as hold down or straps at the edges of the walls, and then along the length at the base of the wall, we have anchor bolts or some type of shear connectors. Now, many of you have utilized software, I'm sure, in the past or are currently doing so to design timber shear walls. So let's talk about some of the challenges when it comes to these software programs that we may find it's typically clunky, it's outdated, it requires these complex modeling workflows. So we may turn to spreadsheets or hand calculations instead. Additionally, we find that software has the inability to consider what we call the 4 sources of deflection. And these are given directly in the SDPWS code in section C434. This would include the end post deformation. So this end post over on the left here may be in tension, so we'll essentially elongate. We also have our end post over here that might be in compression, so we'll essentially shorten. We also want to consider the shear panel deformation. So we're talking about the sheathing itself. The panel nail slip. So in the SDPWS code, this is a nonlinear equation that's given. And finally, we have the wall anchorage deformation. So we're talking about those hold downs and those shear connectors that we had shown on the previous page. And additionally, when we talk about these analytical approaches, shear transfer is typically ignored above and below the openings. In addition, we also have the inability to view shear forces between elements. So for example, when we're talking about the panel nail slip, this is how the sheeting is connecting to those stud elements. We're not necessarily able to see so easily what are these shear forces between these two elements. And finally, common problem with any software is this black box where we essentially don't understand where the program is coming up with the results. It's not so transparent. So we're left wondering, okay, we're not really sure how the program determined these design values. So we're going to revisit this slide at the end of the presentation to see hopefully how we can turn these challenges into solutions with RFEM 6. So we can begin within our program RFEM here that when you create a new model, we are within the base data dialog box. And under this second tab are the various add-ons. And these are optional just depending on your project needs. RFEM, the base program, will allow us to fully model the structure and we can run an analysis. But for the timber shear walls, we do need to take advantage of the multi-layer surfaces add-on. So this will give us the ability to build up these shear wall elements automatically. Now, if we want to take the analysis a step further and carry out the design, we do need the timber design add-on. So both of those are activated here. Under the third tab, this is where we set our standards. We can generate the load combinations automatically according to the ASCE 7. You will see that the option wood is required when we have activated the timber design add-on. And the reason for this is so we can generate the IBC load combinations for serviceability checks to directly consider creep. As far as the timber design add-on itself, we have here the NDS standard and the latest 2024. So when this information is set, we are brought here into the main program. Now, I did generate a couple cross sections as well as a thickness. And my suggestion for the workflow here for our shear wall is to define the cross sections, your panel sheeting that will eventually be used to model this timber shear wall. So let's take a look at these quickly. Starting off first with our cross sections. I do want my inner studs, for example, just to be standard 2x4 members. So we visit our cross section library. We certainly can go ahead and select one of these massive sections here to directly input the actual dimensions, not nominal, but actual, and have the program calculate the cross section properties. Under the standardized section though, you will find that we can utilize our filter to the United States over on the left to the NDS 2024. And we have various cross sections already available, including a 2x4 where the actual dimensions will be modeled within the program. Now we can also assign a material to this cross section. So in a similar manner, we visit the cross section library. Over on the left, we can filter to the US, to the material type timber, and to the 2024 standard. We could take this a step further and see all the available tables here from the NDS. For example, visually graded lumber. We have every single material from the NDS within this material library, including the additional submaterials. For today's example, we'll utilize this Douglas fir South select structural. So for this single 2x4, the cross section is now defined. I also want to do the same for a double 2x4. So we could visit our cross section library here again, utilize the massive options, or we could also take advantage of the built up section. For this, I can tell the program, okay, let's go ahead and use two 2x4s here. We assign the same material to it, and now our two cross sections are defined. You also see here a thickness. So this is going to define our sheathing material and the actual thickness itself that we'll eventually use for that particular surface. So let us go ahead and take a look at the thickness definition. You'll notice that we first need to assign the material, and we go into our library here. And we have under the US, the United States, again, that filter, both OSB and plywood materials. And taking a look at OSB, for example, we have non-structural versus structural. We have the different span ratings. We have the different thicknesses. So let's go back to the PowerPoint to discuss this in a little bit more detail. For all of the OSB and plywood materials, we did refer directly to the 2020 APA panel design specification. And within the APA, of course, OSB and plywood are covered here, but the material properties such as stiffnesses and strengths were actually not directly straightforward. So I'll explain a little bit about how we derive these. You'll notice first that the nominal thickness is given in table 12 in the APA. So we offer then the standard thicknesses, 3/8, 7/16, and so on. The stiffnesses, though, that we need for the stiffness matrix were derived from table 9. And when we look at table 9 within the APA, we are given values here for the different thicknesses, both parallel and perpendicular to the grain. This is just the concept of wood, of course. We have different strengths in different directions. The bending stiffness EI was given in this table. Well, we knew what our thickness was, and we're just taking an arbitrary panel width here of 12 inches. We could back calculate, because now we know I, to determine the modulus of elasticity for bending. And this is what we denote in the program as the modulus of elasticity plate at 0 and plate at 90. So parallel and perpendicular to the grain. We were also given the axial stiffnesses in table 9 based on EA. Again, we could back calculate here, and we could determine the modulus of elasticity, E wall 0 and E wall 90. So again, we have two different stiffnesses used depending if it's in bending or axial. What we denote here as plate or wall. The shear stiffness was given as GT, so function of the thickness. Again, very easy to back calculate to find the in-plane shear modulus GXY. So again, this is the in-plane shear modulus. Now, we were not given the shear modulus GYZ and GXE, so this is into the thickness of the panel itself. So we estimated this as 1/20th of the in-plane shear. Now, this is a given estimate within the Eurocode. The NDS and other US specifications don't really touch on this topic, so that was the approach that we took for this material stiffness. Now, moving on to the strength. So this is great for the analysis, but for the design, once we do get into the timber design add-on, we needed the strengths. These were also given in table 9, of course, parallel and perpendicular to the grain. We could back calculate to determine bending, tension, compression, and shear strengths. Now, both non-structural and structural materials are available in that RFEM library. A couple important notes here when we talk about modeling in RFEM, we do need to modify the material model to orthotropic timber for surfaces. Now, this will make a little bit more sense in just a minute when we get back into the program. Also important is that we're selecting the surface within the material definition, but we actually need to input in, or sorry, we're selecting the thickness within the material definition, but we actually need to input in the thickness when it comes to the RFEM modeling for the surface. So again, this will also make more sense in just a minute. So we will go back to the RFEM model here. And again, we're taking advantage of the OSB. We have populated that particular material here, 0.469 inches. If I go back into the material settings, so the orthotropic timber surfaces material model is selected here. This will ensure that, remember we talked about the modulus of elasticity for bending and axial. These are both taken into consideration for this surface element. When we toggle this to orthotropic linear elastic for just general surfaces, we lose that capability and we only have one input in here for our E values. So we'll go ahead and leave this as orthotropic linear elastic. Now, when this information has been defined, remember I mentioned you do need to define the thickness here. So although we selected it in the material, we need to define it for the actual surface thickness. What is nice is that we can also input in here a fraction. The program will automatically convert it to a decimal for us. Okay, so now that the information has been defined here for our surface thickness as well as our cross sections, notice the materials are given here. We are now ready to create our shear wall. We're going to modify our drawing grid here in the vertical direction. And I'm going to draw a new rectangular surface. So the surface defaults to that OSB thickness and material, but I actually want to create a new thickness type here. And for this one, I'm going to select the thickness type beam panel. The beam panel is only available to me because I have activated the multi-layer surfaces add-on. Without that add-on, I would not have access to this thickness type. So this is where we can begin to generate all of the elements that, again, make up this shear wall. And we begin first with the chords and the plates. Now, if the outer studs, top and bottom plate are all the same cross-section, great. You can select it here from your drop-down, maybe where that cross-section has already been defined in the model. If you want to set them differently, which we do today, we turn on this checkbox and we have a new tab available to us where you'll notice up at the top, we can go ahead and toggle this to that double 2x4 for our top plate. Now for the bottom plate, I'm going to keep this as a single 2x4. But for my chords or my outer studs here, I am going to also modify these to that double 2x4. So essentially the framing elements are done for the outer portions of the shear wall that we move on to the inner studs. We create a new definition type here. We can select, again, it's already defined, those single 2x4s within our dropdown. We specify the spacing of 16 inches on center. We could also specify here an offset to the first stud if we'd like, but everything is quite straightforward there. Now we're going to move on to the sheeting. So if you did have the same sheeting at the front and the back of the wall, we could uncheck this different option and just define that here. But in our case, we'll leave the default option checked on for different. We have a tab up here at the top to define different sheeting for the front versus the back of the wall. So we'll start first with our sheathing definition type here. Now, we've already defined the OSB thickness. It's available in our drop-down box here. We talked in great detail about setting the thickness, the material, everything looks good. Now we specified the sheathing pattern. So case one is just going to be one continuous sheathing across the entire shear wall. We know in reality this might be useful for something like hand calculations, but we likely are going to have something more similar to case two, where we have these different panels set at a sheathing unit width here, spanning in the vertical direction. Now there are other cases here. So for example, case 3 for horizontal placement, or even case 5 with staggered. I would say this likely is not going to be a case that you're going to use right at this moment because we don't quite yet have horizontal blocking for those members. So therefore, the sheathing is not able to attach to the horizontal members. Once we do add that, then of course these different sheathing types will be more applicable. But for now, let's go ahead and utilize case 2 with a standard unit width of 4 feet. So now that definition type is created, it's populated here for my front wall sheathing. I don't want any sheathing in the back, so I can leave this empty. And now we move on to the connectors. So for this one, we do have the beam-to-beam connector. It defaults as hinged. This just means that we are going to release the moment for the member-to-member connections. If you want to modify this or create your own user-defined, you could certainly do so, but it's probably pretty common just to simply release the moment. Now let's move on to the sheathing-to-beam connector. So we're going to create a new definition type here. And this is simply how is the sheathing connected to our member elements. You'll see the connector type is set at nail. We also have a staple available here. This is a little bit more common for Eurocode, or it could be user defined. So in our case today, we are going to go with the nail option. Under the stiffness calculation, we do have the NDS set here. Notice we also have the CSA standard. We are working diligently on completing the timber shear wall design for the CSA standard as well. So just keep that in mind, but for today, we will utilize the NDS. Now, there are several other input options here within this dialog box that I would like to once again go back to the PowerPoint to explain this in more detail. So for the sheathing to stud connectors, we are going to refer to the 2021 SPDWS code to talk about the nailing fastener slip. And within the code, we are given 3 fastener sizes, 3 nail diameters, 6D, 8D, 10D. So this is going to be something that you're going to input directly into this dialog box. Now, we also are going to specify the nail spacing. So perhaps that's something like 6 inches, again, directly within this dialog box. So depending on this information input, we are going to refer to the SPDWS table C423D. And we're going to get much more into this table a little bit later on, but just notice that depending on the fastener size, we do have a fastener slip equation given to us here. It is a nonlinear equation. But this equation is dependent on a couple additional factors, and that's what you'll find at the check boxes down here at the bottom. So the first is to consider the connector stiffness in the longitudinal direction only. Well, the SPDWS addresses slip along the stud length. So this is in the longitudinal direction only. It does not address slip in the transverse direction. So if we're looking at a vertical stud, we can certainly apply this slip along the length of the member, but again, the SPDWS does not address a slip left and right of the member. But you could turn this off to apply this nonlinear slip equation in the transverse directions as well. Again, it's on by default because this is what the SPDWS essentially addresses. The second checkbox is dry lumber. So depending if the lumber is green or dry, of course, we have a slightly different equation here that is set by this checkbox. And finally, we have the structural grade sheathing. Is it structural? Go ahead and leave that checked. If it isn't, go ahead and uncheck it because we do have a 20% slip increase for non-structural sheathing. Now, we are working on improving this in the sense that we know which material you selected from the material library in RFEM. So pretty soon we'll link up those two so you don't have to have this manual checkbox. But until then, you want to ensure that this is set properly. Okay, so we will go back to the RFEM model here. And for our example today, we want 8D nail type. We want the spacing set at 6 inches, and we will leave all of these checkboxes on. And we click OK. So now that this information is input, I really want to highlight the use of templates. We recognize that this does take some effort to input in all of these different elements. When you're done, save this as a template because most likely your timber shear walls are going to utilize these same elements over and over and over. You can create as many templates as you want, and that way for future RFEM models, you can just load directly from these templates that are listed here. So these are my own templates that you can see listed. Again, just a bit of a time saver there. Okay, so once we are done defining this thickness, remember we're still within this draw a new rectangular surface. So I'm going to click OK, and I'm going to snap from the origin point, and I want a 16-foot length and a height of 8 feet. So the program will go ahead and generate this surface element for us. Now, one thing to mention as I hover over this, the y-axis of the surface, the local y-axis is pointed down. This is really important for the timber shear wall input. We want this y-axis to be pointed down. If it's not, you could right click here and reverse the local axis system. You could double click on the axis itself to kind of do some rotation options within the surface dialog box. But again, this needs to face down. Now, also the z-axis, we place sheathing at the front of the wall, not the back of the wall. You want to pay careful attention about the local z-axis as well. So looking at this surface element, it looks pretty standard, just a standard surface element, but we have this feature up here in our toolbar to display the beam panel. And when we activate that, all of those elements that we have defined with that beam panel thickness are now modeled automatically for us. So as we take a look at more detail of these various elements, notice that here is our sheathing. And the sheathing is in 4-foot panel increments. It does need to align with an interior stud, of course, because that's how we connect the sheathing back to the framing objects, but those are all shown. When we look at our member elements, we have our double 2x4 at the top plate, also the end studs. But for the interior studs, these are the single 2x4s at 16 inches on center. And then we also have our bottom plate here, which just is a single 2x4. Now, let us talk about the really powerful thing, though, that's going on with the beam to sheathing connection. So I'm going to turn this into a wireframe view. And when we zoom in here, you'll notice that our member is represented on the left here, and then our surface, our sheathing, is represented by this additional dotted line. These two elements are connected here with what we call a rigid link. And before I get into this, I'm going to go ahead and right click on the line element itself to turn on the local axis system, because this will come into play here with our further discussion about these rigid links. So each line has its own local axis system as well. And let's dive into this rigid link in more detail. So not only is it a rigid link, but it also has this line hinge assigned to it. When we go into the line hinge details, this has 4 degrees of freedom. Again, how the sheathing is connected to this member, to this stud. And we want to first focus here on translation in the local x-axis. So this is the local axis of the line itself in the longitudinal direction. So again, along the length of the member, we have this set to a nonlinear diagram. We can view this diagram directly under this tab where we see here this nonlinear slip from the SPDWS code represented exactly. So for this, I'm going to go to the PowerPoint because perhaps we want to better understand, okay, how is the SPDWS code and these nonlinear equations taken into consideration with this RFEM 6 nonlinear line hinge? Well, remember for our example today that we have 8D nails and they are at 6 inches on spacing. Well, we are going to refer to the SPDWS table C423D. And this is just, again, the table we saw in the previous slide. It's taken directly from the SPDWS code. I just kind of redid it here for this PowerPoint. Well, when we take a look at our particular fastener size, 8D, we have a max fastener load of 220 pounds per fastener before the fastener yield. So that's going to be the top flat point here of our diagram. Now, we also have structural 1-grade sheathing. We have dry lumber. So therefore, the fastener slip here is going to be represented by the equation highlighted in yellow. So I wanted to verify a couple of these points here along this diagram to ensure that it aligns exactly with the SPDWS equation. And we're going to start first with the last point. So this max fastener load before this fastener yields, 220 pounds. Well, as you can see here, we have 220 pounds defined per fastener, but we have 2 fasteners per foot due to the 6-inch spacing. We convert this to inches, and what we'll see here is a total force of 36.667 pounds per inch. And sure enough, that aligns exactly with the value in the table here, the diagram of our nonlinear line hinge in this second column. Well, we're going to further take this 220 pounds and input it into the equation shown in yellow. So when we do this, we get a slip value of 0.0447 inches. And yet again, this aligns exactly with what's written in the table here for the line hinge in the first column for the displacement. So we want to also pick a second point. So not the last point, but the second to last point where the load is now 198 pounds. Well, it's 198 pounds per fastener. Again, 2 fasteners per every foot. We convert this to inches and we get a total force here of 33 pounds per inch. We input in the 198 pounds back into this nonlinear equation shown here in yellow, and we get a total slip now of 0.0325 inches. Well, in order to determine the spring constant between these 2 points, this is just simply the slope in the diagram itself. And we know that we determine slope here as the difference in the rise over the run. We input in all of these values directly into this equation, and ultimately we get a spring value here of 301.035 that again aligns perfectly with our diagram here in RFEM to essentially represent the slope here between these last 2 points. Now, the same concept is followed for a total of 10 points along this nonlinear diagram, again, to represent these nonlinear slip equations from the SPDWS code. All right, so now that we are back in RFEM here, we have verified this nonlinear diagram. And I'll go ahead and cancel out here. We'll turn back off the visibilities of the local axis system of the line. The other thing that I wanted to point out is that you also see these rigid links at the top here, kind of connecting these members back to that general surface view. These are fully rigid. There is no nonlinearity defined for them. And you might be wondering, well, why do these exist? So if we go back to the simplified view here, and let's just highlight this full surface, and I'm going to hold down my control key, and I'm going to drag and drop here to make a copy, maybe on top. I'm also going to continue holding down my control key to make a second copy adjacent. So now I have 3 timber shear walls. Well, I can turn on the detailed display here, and these timber shear walls are going to connect perfectly to each other through these fully rigid links. So this was done with intention so that modeling these adjacent walls will be very easy. Okay, so we'll go ahead and turn off the detailed display. I'll go ahead and undo the copying here so that we get back to our single surface. So now that we have modeled all of the elements, let's talk about the supports. And we want to begin with first just our top support. So I just want to brace this very simply out of plane. I'm going to apply a new line support, and I'm going to keep this in the simplified view. So we'll apply a new line support here. I'm going to create a new definition type. And for this one, I'm just going to support it in the out of plane direction, which would be the global y-axis. I click OK. I can graphically select here my top line. I click OK. And I can hit apply so that the program goes ahead and assigns this line support graphically here in the background, but I'm still remain in this diagram because I want to create a new definition type for the base of the shear wall. And I create here a new definition type, and actually let me also create here this new definition type. And we want to, give me one second, I'm going to actually apply this one to the model. I just want to make sure that that stays. So we'll go back to drawing here a new support type once again, and we create a new support definition type. Oh, I know what I did wrong. I think I did not save here. This one is assigned here to member number 1. I think I went ahead and applied a pinned line support to all of them. So no problem. We can go ahead and graphically select this, and the line support looks good there. Okay, so everything looks fine. For the base of the wall, a new line support yet again. And for this one, I want to create a new definition type where we take into account some nonlinearities. At the base of the structure, I want to go ahead and release this support and uplift. Well, because RFEM is a nonlinear analysis program, we have the ability to set this failure if we have a positive uplift force. Now, in the translation directions, notice I leave rotation free here. In the translation, especially in the global X direction, this could be a scenario where you contact the manufacturer for your anchor bolts or whatever it may be, that if you want to account for maybe a spring constant, or you could define your own diagrams if you would like to go ahead and input in some slip there as well. That's certainly possible. Now for today, we're going to keep this pretty simple, which is the failure of positive Z. All the rest are fully fixed. Okay, so now that we have created this new line definition for the support, we'll click on line number 4. Okay, so it's blue because it is nonlinear there. So everything looks good. Now let's talk about the hold downs. So for the hold downs, we want to model these as nodal supports. And I would suggest here that we activate this detailed view because these hold downs are typically placed at these end studs directly. So I'm going to create a new nodal support. And I'll go ahead and create a new definition type. That's fine, or I could modify one of the default definitions. This is going to be restrained here in the translation directions only. Yet again, same concept of what I talked about. We can always apply spring constants, nonlinearities if we want, but for today's example, we will keep this as just a general pin support. I click OK, and then we would zoom in here to our outer stud to apply that at the bottom node of the stud itself. So that should take over those tension forces when this bottom line support fails. Okay, if these seem a little bit too big, you can always right click to decrease the size using the slider option that we show here graphically when you right click on the support element itself. Now moving on to loading, now that the modeling process is complete. So within our load cases and combinations, remember we're generating these load combinations automatically according to the ASCE 7. I created a couple simple load cases here for dead load and wind load only with the relevant action categories set. The program will automatically generate the design situations for LRFD load combinations, ASD load combinations, as well as IBC for serviceability. Today, I am going to carry out the design according to ASD, so I can simply deactivate here LRFD, or we could delete it altogether. But we will leave the ASD active for strength design checks and serviceability for our IBC load combinations. Jumping to the load combinations tab itself, we see these all listed out here individually. So these belong to the first design situation in red for ASD strength, and then we have our IBC load combinations here in yellow. So now that this information is set, we want to actually apply the loads to this wall. And we're going to go back to the dead load here and the simplified view. For the dead load, I will apply a new line load. And a line load is typically applied to surfaces, not to be confused with member loads right next to it. This will be a value of negative 0.05 kips per feet. And I can graphically select the top line here. I click OK. It's applied in the global Z downward direction. I can hit apply and next. So this way I remain within this dialog box here, but we can see it applied in the background. Well, now I can toggle here to wind load. And I'd like to modify this in the global X direction. So I can see that based on the global axes here in the background. I'm going to modify the magnitude here to 0.25 kip per feet. And I can graphically, once again, select this top line and I can click OK. So very simple loading for today's example. Now, I actually am ready to run the analysis with all the load cases, with all the load combinations, but for simplicity, I'm just going to take a look at the results here for a single load case, just wind load only. Now, what the program's doing, you notice that we still just have this general overview of the surface element alone, not all of the different framing elements, the sheathing, but those exist in the background for our calculation. So once this is done with the calculation for the wind load case, we can display the detailed model. And now we're seeing here in our navigator the global deformation. So let me turn off the display here of the FE mesh. And you'll see that we have the ability here to increase the factor. We see the contour lines and we see the separate panels here modeled at 4-foot widths, considering that nonlinear line hinge that we discussed within the PowerPoint. But in addition to the sheathing, of course, we have our members that are deflecting. Now, if we'd like to change the view of the members, we can come on here to deformation and change these to colored cross sections. And maybe we'd like to set the display here of the ISO bands a little bit nicer with a smooth color transition. So everything looks quite good there. So based on this applied wind load, maybe we want to look at deformations only in the X direction, and we see a total value here of 0.0772 inches. So not very high, but this entire system is working together. Just like what we talked about with the deformations from the PowerPoint and the SPIDWIZ, those 4 different points. We have the nonlinearities for the line hinges. We have the sheathing, the different panel widths. Again, everything acting together to determine these deformations that we see here. So in addition to the deformations, let's talk about some of the other results available to us, such as the surface results. Now, we can design the sheathing. And for the analysis, though, we're probably most interested in the stresses tau xy. So this is going to show the shear in-plane stresses of my sheathing material, taking into account the shear deformation. In addition to the surfaces, we also have the internal forces of our members, and perhaps we'd be a little bit interested in the axial forces. And as we would expect, looking at these axial forces, we have a pretty high tension force for our outer stud on the left, and we have a pretty high compression force for our stud over here on the right due to that overturning effect. Now we can further take a look at the support reactions. So we'll begin with first with only our nodal supports. So within the nodal supports, maybe I deactivate X and Y. I'm only looking at the supports in the global Z direction. So we have here a tension force. I know it's a little bit difficult to see because it kind of overlaps with that vertical stud. We have our compression force. And if it's not so visible graphically, of course, everything is available in table format. So we look at the static analysis, we look at the results by node, and we see the support forces here in the vertical direction. This is what we would design our hold down for. Notice we have a nice arrow here showing you exactly where you're at within the table. So taking a look also at the line supports, and in this case, I'm going to modify this to the global axes. And I'm probably interested in the shear forces along the length of the wall in the global X direction. So I can display these graphically, but I can right click on the support itself and view what we call the results diagram. So this is going to show me a little bit more information about those shear forces along the length. We have the ability here to display the linear smoothing, which is going to give me the total shear force or the total shear force as a unit of length. This is what would be used to design those anchor bolts or those shear connectors. And finally, after looking at our support reactions, let us also display what we call the releases. So we're going to turn on the releases for the line hinges themselves, and we're going to activate here forces for N. This is going to be the shear flow of the forces between our framing elements and our sheathing. And it's shown graphically here. Notice up at the top, remember we applied this unit load here, or this load along the length of the shear wall, a 0.25 kip per feet. Well, you'll see here that this matches pretty closely. We can further do some options down here at the bottom in terms of our display. So for example, if I don't want to show the actual shear forces, but I'd like to smooth these out a little bit based on the constant mean value, this is also possible. So we can play around with these options here. Now, it's not exactly 0.25 kips per foot because we don't really have an ideal shear panel here when we're talking about hand calculations. When we look at hand calculations, we're really only considering the end studs. We're further not considering the inner studs here. We are also not considering these nonlinear equations, essentially for our slip of our connections. And also remember, these shear wall panels are not one continuous sheathing, or sorry, the sheathing panels themselves are not one continuous sheathing, but they are in those 4-foot increments all modeled here. So all of these come into play with true FEA. So that's why we might see slightly different forces here for our shear force, again, versus something like hand calculations. All right, so now that we have addressed the analysis, let us talk about the design. And to begin with, for design, we need to input in a little bit more information specific to these NDS and SPDWS code design checks. And I'll start off with first with all my vertical members. So I can highlight everything vertically here, and I can right click, and under the members, we can go ahead and edit these. The reason why is for our members, we are required to input in information like unbraced lengths. And we do so under the Design Types tab. So I create a new effective length definition, And you can see here for these vertical studs, I'm probably not interested in checking buckling in the weak axis. I'm also not interested in lateral torsional buckling. We have this sheathing that is fully connected to all of these members, that this is not a failure mode that we need to be concerned with. But we do want to check flexural buckling about the strong axis. So we'll go ahead and leave that active. So we can input in all this information for our vertical members. Now my horizontal top and bottom plate, I'm not concerned with buckling here. We likely have a floor framing in addition, the bottom plate here is going to be connected directly to our foundation. So buckling is not so much a concern. So we can simply not assign an effective length to those members. Now, let's also remember from our analysis that when we turned on the axial forces for the members themselves, we have a pretty high compression force over here on the right-hand side. And when we look at the two members here, so I'll create a visibility and we'll go ahead and render this so that we can see this a little bit more clearly. This vertical end stud is framing directly on top of the bottom plate element. And we have the ability in RFEM to do an additional design check in the timber design add-on for compression perpendicular to the grain. And I'm pretty sure there's not a whole lot of software, if any, out there that can do this additional check. So how we go ahead and define this is by double clicking on our bottom member here. And we have a tab called Design Supports and Deflection. So I'm going to go ahead and create a new design support at this very last, second to last node, last node here that you see shown graphically. And for this node, we are going to create a new design support. And it's not going to be in the strong axis. We're going to apply this in the weak, the local Y axis. We do want to specify here the support length. And what this is just simply the width of the member, that vertical member framing into the top of this bottom plate. So this is a total of 3 inches just based on the cross section itself. So when that information is input, we get a little design support symbol here, but we do get a new tab. And this new tab is where we can specify, okay, which members versus which forces should we be looking at for this additional check, compression perpendicular to the grain? Well, we're looking at the axial force here of our vertical member. So that's denoted here by N. Now, all other forces, such as shear forces, including the forces at the bottom member, are not of concern. We only want to look at the axial force, again, kind of framing into our bottom member there. So once this information is defined here, there's one more thing that I just want to cover. And we're going to go over within our navigator here, and I can collapse all these folders. The timber design folder has our strength configurations. So this is only available, again, because that timber design add-on is activated. And with the configuration settings, we have a new tab here for beam panels. The beam panels tab is just, again, none of this affects the analysis. This is purely for the design once we get into the timber design add-on. And we start off with first here the design of the connectors. So again, that sheathing to beam fastener, we can actually design once we do get into that add-on. The first option here is the connector force N. This is exactly what I just showed you graphically from that wind load case, where we could view that. We could smooth it out either based on linear or constant, or we could have no smoothing. So the exact same settings here, you just need to tell the program what you want to use exactly for design. Now we also see a connector force VZ. And this is related, if you remember back to the PowerPoint where we had that first checkbox when we were defining our connector settings, that if we wanted to consider the nonlinear slip in the transverse directions, this is VZ. In our case today, we did not activate that because we left that checkbox turned on. So therefore, this is not relevant. Now we are going to refer here to the SPDWS table 4.3a for the connector capacities, and we'll get into this in a PowerPoint slide in just a minute. The only other thing worth mentioning here as well is the member design. So of course we have strength configurations for the members as well. You might see an error with the torsion being over the default limit here. As we know, when we refer to the NDS, torsion's not so clearly addressed. So we do have an option here to design our members for torsion according to the timber construction manual. This might be a suggestion if you want to maybe take a closer look at the torsion design checks according to this manual, again, since the NDS is not so clear. Okay, so now that we have set these configuration settings, we jump down to the timber design add-on. And we can do so within the table here. We see our design situations. ASD is set here to the strength limit state for ASD. Serviceability, IBC load combinations are set for serviceability or deflection checks. So go ahead and cancel out this visibility here. And under the objects to design, you'll notice that we have all the different objects here that we can design, including members and surfaces, but we also have here beam panels. So I can go ahead and only activate the beam panels. The reason why is that the program's intelligent enough to know, okay, if I want to design this beam panel or the shear wall, I know I need to also design the members, the sheathing, the connectors, everything will go into it. And when that calculation is done, we are now presented with the results within the timber design add-on for the actual design of all of these elements. So let us start off with first the design of the members. And we'll go into a wireframe view here where we can see the design ratio shown graphically. And within table format, we can jump to design ratios by member. Now, what's nice is that I can graphically click on a member. It will immediately jump to that particular section within the table. And remember, we're checking that additional compression perpendicular to the grain. Well, the big red arrow shows me exactly where we're checking that. Surely that makes sense. That's where we applied our design support. And we can view here all of the design check equations directly from the NDS. So very transparent here in the equations used, the variables, any adjustment factors, code references, and how ultimately we came up with this design ratio. And the same is true for every single design check for every single member within this shear wall. So jumping now to the design of the sheathings, remember from the first PowerPoint slide talking about the OSB and plywood capacities or the strengths that we determined from the APA specification. These are taken into consideration here for our surface design. So we can design each individual sheathing panel here. We can look at an envelope solution. Probably what's of most interest is going to be the shear in the XY plane. So that in plane shear, again, we're comparing to the tau XY stresses from the analysis. Now, the final topic in the design check here is the connectors. So we are checking every single connection between the member and the sheathing. And we see here only one single design check. Well, within these design checks, we can yet again visit the design check details. So to explain this a little bit further, the demand force here in kip per feet is taken from the analysis. And this, again, is exactly what we viewed when we viewed the wind load case. I displayed the releases. I displayed that internal force N. That is the shear flow between these two elements. So that's the demand. Now, as far as the capacity, we get this directly from the SPDWS code. So I'll jump to the PowerPoint yet again to talk a little bit more about the sheathing to stud connectors for the connector shear capacity. This comes from table 4.3a. And I did take a little screenshot here of this table directly from the SPDWS code. This isn't the full table, it's just a little part of it that's relevant for our example today. But it's worth explaining this in a little bit more detail so you understand where the capacity of these fasteners, of these nails, is coming from. So we begin with first our panel. So we want to choose here the sheathing material. Is it structural? Is it non-structural? We would find our thickness that we're using for our shear wall. And a few things to note about this is that if you're using a thickness less than the table value, you will get a design error for this connector design because the SPDWS code says, hey, that thickness is not allowed. You would need to size up. Now, if you're using a sheathing thickness that's greater than the table value, then what we're going to do internally in the design checks is the conservative approach and round down. So for example, if you're using 1930 seconds, we would round down to give you the capacity for 1530 seconds. So that's important to understand. Now, we also talk about our nailing itself. So we start off with first the size of our nail. In this case, it was 8D. And then you will notice that we have the different spacings in the columns here. So the only spacings that are given are 6, 4, 3, and 2. If you have defined in RFEM a spacing that isn't in between these values, so for example, 3.5 inches, or if you defined here 5 inches, we're always going to round down to the closest value that's given here directly in the table. If you use a nail spacing greater than 6 inches, you're going to get a design error. SPDWS code does not allow this, so therefore neither does RFEM. Then finally, if you're using a spacing less than 2 inches, again, we take the conservative approach and we will just use the capacity here for 2 inches. Now, there are several table notes that are given within the SPDWS code underneath table 4.3a. These are also considered within RFEM. So, you see these different notes that are given here. This is directly considered within the capacities. So ultimately, after we consider all the highlighted blue options here within our particular example today, we get a capacity. And looking at 6 inches spacing, we see 785 pounds per foot. Looking at the RFEM results here, we see that capacity directly given in kip per feet, 0.785. All right, so going back into RFEM then, this just gives a nice summary then of all of the design together for this entire shear wall. Now, probably a very common question is, hey, how is this handling openings? So let us go ahead and deactivate here the results. And I'm going to display this simplified view here. And we want to add in some just basic openings. Well, we can do so with the new openings option up here in our toolbar. And I create a new rectangular opening and we could snap here from a couple different points. Really doesn't matter, just for example purposes. We have to delete our results here. We also want to create a door opening, so we can go ahead and snap to maybe a different point here. And we have our couple openings. So when I turn this into a rendered view, looks great, right, for our simplified surface. But when I display the detailed view of my timber shear wall, not so great. We have our vertical studs running right through those openings, and it more or less looks like a jail cell. So how can we get the program to automatically detect these openings for all of our framing? I'm going to go back to this simplified view here, and we have a really easy and great function that I can right click once I've inserted in those openings. And we have here what's called create surface cells due to openings. And we apply this in the vertical local Y direction of our surface itself. And when we do this, you'll notice here in wireframe view, the program has placed these different cells at each of these locations around the openings. And now when I display the detailed view, and we'll go back to a nice rendered view here, we're going to see the framing automatically consider those openings. Now, if we wanted to maybe make some changes here. So for example, the exact same settings from my overall beam panel is going to be used at every cell location here. But let's say for the locations above the openings that I want to modify, for example, the header, maybe the cross section, the size, whatever it may be. I can hold down my control key to select both of these cells. And I can go ahead and double click to edit them. We have a function here where we can overwrite the thickness, the surface thickness, with another thickness. So I can create a new definition type here, and I actually don't want to use the default definition type. I'm going to go ahead and delete that. But again, we can always take advantage here of our templates, right? If we have this already defined, we could load a template. In my case today, maybe I just make a copy of my existing beam panel thickness. I jump over here to my beam panel tab, and for the particular beams, I want to modify here what is the bottom plate of my, which is essentially my header above my opening. Well, I'm going to go ahead and edit my cross sections here. And my double 2x4, I'm going to make a copy of this one, but I want to rotate it 90 degrees. So we'll go ahead and rotate it 90 degrees. I click OK. We select this from our drop-down box here. So everything else remains the same. When I click OK through all of these settings, now we have a header oriented in the vertical direction here above my openings. So this is just a nice, quick, easy way to modify these surface cells if you want to make quick changes to the layout of your beam panel without having to redo all of, or maybe redefine separate beam panels for each of these locations. Certainly work with those particular cells. Now, we do want to delete the support here. We don't have any support, of course, where our opening is. And then we also lost our hold downs. This is just because we assigned them originally to that node for our vertical studs at the edges. So what we can do here is go back to a wireframe view. We can create a new support definition, again, just using that same support I've already defined. I click OK, and I can go ahead and click on the outer stud. And then, of course, we'd probably want to place a hold down here at the left of our wall, or sorry, at the left of our door opening, the right of our door opening, and then maybe one more at the end of our wall on the right side. So once all of this is done, we still have the same applied loads to the structure. Nothing's changed there. And we could quickly take a look at our design results. Really identical workflows here. The one thing I will say, we did lose the effective length, those unbraced lengths for our vertical members. We would want to redefine them. Again, we made some changes to our layout, maybe unbraced lengths change. So essentially here, we could reassign those and then again get full design of our members, surfaces, and our connectors. You'll notice that if we jump down to the design of the sheathings, this is a pretty common problem when we talk about FEA analysis, is that we get really high stresses here at the sharp corners of our opening. And remember, we're applying FEA. These are not analytical approaches here to the timber shear wall. So it is FEA. What we would typically do here is apply something like an FE mesh refinement. We also have what we call surface result adjustments, just to smooth out these high peak forces that we know really don't exist. Well, a couple other options too is that when we refer to the connector design from the SPDWS code and the connector or the fastener capacity, the code has also done the research to ensure that the sheathing is not failing. So technically, by doing the connector design, we're also carrying out the sheathing design, because again, all of those tests have been carried out that have been taken into consideration with the sheathing itself. So we could essentially turn off the design of the sheathings altogether within the timber add-on. I'll show you right now how you can do that as well as an additional option. So back under the global settings, again, if you have no interest in designing the sheathing, you can turn that off. Also, there is this feature here under the smoothing settings. So this is typically set to continuous within surfaces and surface sets. Let's change this to constant on mesh elements. So to me, this is just a very quick, easy fix to this singularity problem, in the sense that we're no longer going to try and tie together all of the results here with nice colored contours, but we're giving you exactly one result here per FE mesh element. So this could certainly be, again, a very quick kind of Band-Aid fix to those singularity issues. Now we see there are a couple locations that are still slightly over 1.0, but for the most part, our design check looks quite a bit better. But probably best approach is the FE mesh refinements, again with the surface result adjustments. Okay, so real quick before we jump into the conclusion, I just want to show you guys one more thing for consideration, and this is with an already saved model. There are typically, not typically, but there could be occasionally platform framing, right? Where these walls are not connected directly to each other, but we want to consider some type of gap or distance here in the vertical directions from floor to floor. Well, we can easily do this by creating our own rigid links. So you can see here rigid links are found in the special objects folder in our navigator. It's super easy to connect this line to this line with just a fully rigid link. Again, no nonlinearities to consider something like platform framing. The other thing that I really wanted to mention too is when we're talking about wall elements framing in, 90 degrees to each other, such as this scenario, it is suggested in the current state that you do model a slight gap here to account for just a small distance. Again, connecting this with the rigid links. The reason why is because when I turn this into the detailed view, and maybe I'll even go to the rendered view here, solid, is that everything lines up perfectly. This is almost like a BIM approach to the modeling here. The reason why is because if we had interior sheathing, we would see that overlapping if we fully connected the two panels at a single line element, which could cause issues in the program. Now, we want to continue improving on this topic, but until then, again, you can model a simple gap here and connect those with your own rigid link. All right, so we will go back to the PowerPoint here just to wrap up. So you remember that first slide that we talked about, common design challenges. So I wanted to revisit that with now our solutions that we have in RFEM 6 for wood shear wall design. You saw just the automated features for modeling of studs, sheathing connectors, working with the templates with those different cells. We have high-end graphics so you can see exactly how these members are framing into each other. And also referring to the SPDWS and those 4 sources of deflection, all of these are considered within RFEM. So the end post deformation, of course, with just general FEA, shear panel deformation. We talked about some of the shear forces that we see from the shear stresses from the analysis. Panel nail slip, we saw this with the nonlinear line hinges that are automatically generated based on the SPDWS code. Wall anchorage deformation, so hold downs, those shear connectors, those anchor bolts, these can all be modified here with spring constants. You can define your own diagrams as well for the nail slip, and all of these work together as a system. Now, the shear transfer being ignored above and below openings, or maybe in very small widths between openings with analytical approaches. Well, again, we're using FEA, so we're going to consider the shear transfer above and below openings as well. Also, inability to view shear forces. Of course, we saw, this great graphical, but also table output, being able to view what the shear forces are between the sheathing to panels. And finally, RFEM 6 is certainly the opposite of a black box. We're trying to give you as a user as much information as possible with code references, the formulas, all the variables, and ultimately how these design checks are calculated within the program. As far as future developments, again, we are working diligently on completing the Canadian CSA 086 timber shear wall. So we're almost there. You can keep an eye out for that in the very near future. We also want to work toward the SPDWS diaphragm design. So there are slightly different capacities when we talk about diaphragms, floors versus vertical shear walls. So that is something we are also working towards. We already talked about the horizontal blocking members. So this would be important for something like diaphragms where our sheathing is laid out horizontally. Gypsum materials we also want to add. We recognize not only OSB and plywood are used, but also gypsum. Also, gable shear walls, so different shapes. Right now, we are limited to rectangular shapes only, which covers most cases, but there is the occasional case where we need some of these other shapes, such as triangles. We talked about wall to wall and wall to floor modeling improvements. So we're talking about when the sheathing is overlapping for walls at 90 degrees, for example. Again, we want to continue improving that just to make it a little bit more user friendly for you. And finally, a long-term development here is, and I'm sure going to be requested, is how do we design these hold downs automatically, these shear connectors automatically based on different manufacturer products. So we do have a new add-on called components where we want to integrate all of these manufacturers' products, link them up to the timber shear wall design to give you exactly that, the automatic design of those anchorage systems. So something to look forward to as well. So if you liked what you saw today for the timber shear wall design and you're interested to chat a little bit more about it with us, we could set you up with the 90-day trial version, its full capability. To do your own testing, we would love if you would contact our sales team. So our contact info to our Philadelphia office is at the bottom of the screen, both our phone number and our email. Also, this QR code will take you directly to our website where you can fill out an online form and we can certainly reach out to you there. We will have many more upcoming webinars. We try and hold these approximately once per month. You can register at dlubal.com under support and training webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so keep an eye out for that next webinar. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So I mean, at least 60 minutes in duration, you will receive a PDH certificate. It is the states that we are pre-approved providers require you to be on here for that full 1 hour duration in order to receive that one PDH. If you watched in a conference type setting, or you watched with a colleague and you yourself did not register through GoToWebinar, you will need to request PDH at the email address shown here, info-us@dlubal.com. So again, if you yourself did not register, you were here for the full duration, send us an email, let us know who you watched it with, and we will be happy to issue that PDH to you. This is not instantaneous once the webinar ends. It usually takes us a day or two to get those out. So that will come through your email once those are completed. And with that said, I want to thank everyone for attending today. There will be a short survey that pops up. It's a really big help to us if you just give us feedback on what you think about this new timber shear wall design or the presentation. We're always looking to improve on things. So with that said, thanks again, and we hope to see you at the next presentation.